right. So I got this binary. I mean, if you want to follow along, I can also share the link for it. It's just a crackme, just a simple crackme, but it's the from crackmes.one, the goal of it is just to show you the structure and how binary works in Windows. So is this one bricked up? But you can pick any. I mean, it's just or open up or open a P file. It's just the same. So that's and the password is gonna be crackmes.one, of course. Crackmes.one. Let's see. For all of the crackmes from crackmes.one, that's a secret password. In any case, let's open this in XMP2 debugger, and also let's open it on IDA. So we're gonna do both. So let's begin with IDA. And this is opening this binary just to warm up our end chains, right? So I can show you how a binary works, how it is debugged, the process of understanding what a binary does. That's why it's so important that if you want to become an exploit developer, you also invest some time into reversing as well. It will make your life easier. All right. So first thing first, we need to tell IDA what type of processor this binary has been compiled into, because well, all the type of disassembly that it wants us to use. So we're gonna use Meta PC in this case because it's gonna disassemble all opcodes, and it's gonna cover the majority of it. And then, of course, in IDA, we can process the resources, the parts of the binary, we can say, manually, if we click here, or we can say, okay, unload everything there, including the resources. We can also pass some options for kernel, processor options as well, if you want it. In this case, we're gonna choose let it be just like it is. We don't need to load the resources or manual load. In some cases, it will be necessary in advanced reversing binaries. For example, if you are decrypting something or you are doing some malware analysis, then of course it will be necessary. In this case, it's asking us because it found some debug information. Do you want to load it? We can say yes. And then automatically on this, and remember, this is not for IDA, what we are trying to cover here. But in any case, if you want to take a look into IDA, there is a free version you can get via IDA free version. You can download it. It will allow you to use 32 and 64 applications, so you can actually do what I'm doing here. Let me change the color so it's easier for you to read. Yeah, that's way better. So what I'm gonna say now applies to any debugger, right? So first, the debugger is gonna try to find the correct names for each function that has been detected by the disassembler or debugger on the binary itself. So in the case that doesn't find the correct name, then it's gonna assign a memory position. It's gonna assign a name to it, right? So the name is gonna be the offset of where that function has been found. In this case, well, IDA has discovered everything. It's quite good at that. And then if, as I mentioned, if it hasn't been able to do that, then it's gonna assign choose a memory offset name. But for example, here we can see already the main function. That's of course the main function of the binary. It's gonna start. And then the rest of the functions that this binary is using puts to show something in the screen, is using string compare, it's using scanf to scan for a line, it's using printf again to show something in the screen, it's using signal to check for a signal, might be for the exit as well, memcopy to copy something from memory, abort, C allocation, free to free memory, and so on. And these are the functions that are used externally as well. So, for instance, it's using get process memory, get model handle, exit process, and so on. If we want to see from where this is happening, we can look into imports. So you can see here that I have the function name plus the libraries. Where are these coming from? As I should say at the end, these are externally being called because these are from the kernel 32 library. Here you have them. And from MS BCRT, that's basically one of the most common libraries. Well, it's calling all this from this DLL, of course. All right, and then the exports will be the main entry that is gonna kick the main entry of the program, and then at the end of it is gonna end up calling the main and starting the main part of the program. An hexadecimal view, and of course, at some point, your debugger is gonna show you something on the screen here in the main screen beside the functions. IDA shows you the main if it has been found, and it shows you the main as blocks on the screen with flows to them. It depends on the debugger that you are using, if you have the type of graphical screen or not. In most of the cases you do, or you have a plugin for it. Because this type of screen is quite useful if you want to follow the stream of the program. So in this case, at some point, we ended up here in main, goes the follow like this, and some point it goes a condition that is this jump, and then the program can go into either way, so here or here, and this is quite simple. Because this is a simple crackme, it will be okay or not okay. So it depending on this condition, right? And how do you fulfill this condition is based on what is happening, just happened before, right? Because remember, well, with IDA, I have a way of showing you the code because it has pseudocode disassembler. But you can do the same with other tools. I think there is a plugin for that for x64, and there is Hydra as well. It has a cool open source disassembler into pseudo C. And here you can see in pseudo C, well, this is pseudo C. I mean, it can be compiled, but it's not exactly, it's a representation of what it looks like in C based on the assembly code that we have here. But I'm showing you here so you can understand the flow of this program. I'm going to put it here on the screen so you can understand the flow of the, can I move this? Yes. So you can understand the flow of this program. Here's the main function. And with IDA, if we synchronize the views, if I click on main in assembly, I can see here, and I can see on the pseudocode the exact the same location being in pseudo C. This is automatically done in Hydra, so you don't have to do it in IDA. So you can do exactly the same in Hydra if you want. And if you don't know what Hydra is, this is Hydra. It has been developed by the NSA and is one of the most future-rich open source disassemblers. And you can have it for Windows, Linux. I think also should run on Mac because it's Java based. In any case, I was showing you the flow of a program. So here it is. So first start on main, then it goes into printf. Here you can see we have jumped from here, from call to main, directly when you go to printf to here, right? Because in assembly, before calling the function printf, you have to set up the requirements for printf. In this case, is at least giving the input into here and into this pointer, and then when you call printf, this will be in memory already. So when we go to scanf function is the same. First, you have to go to LIA, that is load. You will load into memory the values that you got here, and then you will put it into EIX, then you move it here, and so on. If you are not savvy with the opcodes, you can in IDA and in JIDA you can do exactly the same. You can add the comments, and then it will just give you the name of what it means, each opcode. Well, not for move, because of course it's move, or sub, and basically the math functions. But for example, LIA, that it means it stands for lowest effective address. So it will move this address from right to left. It's always right to left, and then EIX to here, and then the value is going to be moved here, and then at the end of it is going to call the procedure. So it's going to call the function scanf, and then inside the scanf, it will have already in memory the values that it needs to do the scanf. Then it will do a string copy. So it will move this, that at the end of it, you understand this stands for this string. But in assembly, here you can see it quite easy, because string copy is basically copying this hard-coded string into the variable string1. But in assembly, it looks like this. So you are seeing the hexadecimal representation. I'm pressing the letter R in IDA to change the representation. So you see it's divided in 3, and then it's constructing this string because it's moving the values along to the corresponding memory space, assigning the values from hexadecimal that are hard-coded in memory to a pointer, and then constructing this string. And then at the end of it is loading that effective address. He's doing a mem set, and then at the end of it is comparing these two strings using string comp. And then the value of string comp, it will go as an output. It will go into a register, and then it will call the sham, that is the if here, and then the sham will compare the result from string copy based on the register. In this case, is 0 set f, and then if it's 0, then it's gonna jump. If not, it's gonna go to the other do not occur. All right. So that's how it works. And if you want to debug it, it's gonna be like that. And then as soon as I run the program, what happens is that I see here in IDA, what I see here is the debugger screen. If I pause it, you see that I'm back into the disassembly screen that we were just talking about. But as soon as I press play, it will go into one of these debuggers, because IDA can do remote debuggers as well. as local debuggers, but it will go with the local window debuggers if I press play, because that's the default one. It's going to run the application and it's going to change the screen. And what is showing me here is where I am now, here in this view of the EIP. And then the general registers, because the application is actually running, is not showing anything. And then the modules that have been loaded, the threads that have been spawned, quick representation of the stack in the stack view. And remember, the stack goes from the top. And then the X view of something. In this case, it is the stack, but you can change it or synchronize it with anything you wanted. For the hexadecimal view, hexa representation of the stack in this case. But if you wanted, you can choose do anything else or link it to something else. The output of the program, a Python shell. And I think that's it. Well, of course, you can add more screens to it, whatever you need it. There are a bunch of them. One of the that you should be using is the breakpoint list. So you can also have a breakpoint there, so you can stop. Let's choose do that, and then we're gonna move into x64 so you can see the differences. All right, so let's put a breakpoint. So we're going back into, I just close the pseudocode. I'm going back here. I'm gonna double click on main. I'm gonna put a breakpoint in the first push EBP. So I press F2, I set a breakpoint right there at the beginning. We're gonna press play, and then it's gonna stop there. It's showing you in this debug window. It was showing you the pseudo C code. So we're gonna push here, and then we're gonna continue execution. And then, as you can see, we can continue execution. It's going to ask for a password. It's setting up this here. And then it's going to move the values. In this case, for us, it's going to be 4 A's. And then we can see the value of what is actually the serial code. So we're going to stop it, continue execution, and then that's the correct password. All right. So what we're gonna do now, guys, I'm gonna give you a few minutes. Yes, I was just printing that. Awesome. So I'm gonna give you a few minutes to finally installing the tools. And as soon as we are back, let's say 10 minutes, 15 minutes, please let me know in the chat or unmute yourself if you have any questions about installing the platform, so we can, once you have it, we will do the same exercise in x64 debugger. So exactly loading this binary in x64 debugger, and then from there, we're gonna, as soon as we finish with that, we're gonna jump into the exploit. All right, so I give you 10-15 minutes, and then we're gonna come back.